Hello. My name is Natalie, and as you might be able to tell from the accent, I'm part of the Git community in London. I'm a co-founder of GitLip, which is an AI multiplayer, mobile-friendly developer power tool. And today I'm going to talk to you about building a serverless Git server, which is something we've done in order to realize this product. So I'm going to talk about our journey, our tech, and most of all, I want to share with you our most important Git-related learnings. So Git is immensely useful as a tool for versioning software, but when I think about what makes Git great, I first think about Git's architecture and internals, and not necessarily about Git's interfaces. So my co-founder and I are long-term Git enthusiasts, and throughout our careers, we noticed that Git is underutilized outside of a software versioning context, meaning that there are likely opportunities for building compelling products utilizing Git. So I recently got acquainted with the term Git maximalism. This is from Jonas Tempelstein, who co-founded Monzo Bank and has recently founded iterate.com. And I'm fairly sure we have many Git maximalists here today. I think our views fit this label of Git maximalism as well. I think Git should have a wider application than it has today, or in other words, we tend to view Git more as a protocol for versioning many different types of data and not just source code. So that's how GitLip came about. We thought to ourselves, there are already beloved worldwide Git platforms, and their products are tailored specifically to software engineers. And we wondered, what would a note-taking app or a headless CMS or a personal CRM look like if they were built with Git at their core and utilizing Git as a protocol, leveraging the existing familiarity and enthusiasm of the developer community. And we knew we wanted to build a Git platform of some sort, and since we're also big fans of serverless in general, we were also certain that we didn't want to manage servers ourselves. So before diving into the specifics of our implementation, I would briefly like to talk to you about serverless architectures and our experiences with them. For the purposes of this talk, to avoid kind of discussing semantics, I'll define serverless as someone else is running the service for us, and we get a simple API to deploy our app. So, everyone in the room, I'm curious to know, kind of show of hands, who here is a fan of serverless? Okay. And who here is a fan of functional programming? So Haskell's got, okay, there's more functional programming fans in the room. So the main reason that serverless is so compelling to us is because it's very reminiscent of functional programming. In particular, functional programming is very focused on isolating and correctly managing the state of an application. And similarly, when building serverless applications, one has to reason very carefully about the state. We've been building serverless apps for almost a decade, and we've tried almost all of the platforms in the space. With most serverless platforms, it's trivial to write stateless applications. Stateful applications, however, not so much. There are many issues that one could raise with serverless and state management. So pooling connections to traditional databases who weren't built with serverless in mind, the complexity and the unreliability of network file systems, and the crude semantics of object storage projects, which are insufficient for transactional tasks, so consistency, latency, random access rights, etc. So, disclaimer, I'm not affiliated with Cloudflare, we're just happy customers. So the Cloudflare Workers platform is the first serverless platform that really made sense to us. I'll give a quick rundown of Cloudflare Workers, which will be important for context. So it's a low-latency JavaScript V8-based runtime. No cold starts, single CPU thread, 128 megabytes of memory, up to 10 megabytes of JavaScript code per worker, and each worker is globally deployed. So users across the planet are served by a data center that is close to them. It supports NPM packages, web standards, TypeScript, WebAssembly, and Python, and these are unavoidable essentials for creating production-ready apps. It has service bindings via RPC for easy composition. This is a way to connect one worker to another worker or connect a worker to other services like image transformation, storage, and browser scraping. It provides storage services, so similar to other cloud platforms. Cloudflare has R2 for object storage, KV, low latency, globally distributed key value store, and then D1, a SQL database based on SQLite. But most interestingly, Cloudflare has introduced a new type of storage, which is perfect for serverless, and that is durable objects. Durable objects are what really got us thinking about building a serverless Git server. So the best way to think about durable objects is that they are a mini computer that is single-threaded and has 128 megabytes of memory, has access to a strongly consistent transactional storage, and you can easily spawn millions of them distributed across the world. So the life cycle of a durable object is very interesting. It instantly gets booted up on an incoming request. No cold starts of the worker runtime helps here. It remains in the active state while processing the request and for a few seconds after. And in certain cases involving WebSockets, after about 10 seconds, it might be hibernated, otherwise it gets evicted from memory. So this primitive of a serverless mini computer that we can have arbitrarily many of was very, very interesting to us. And if durable objects seem interesting to you, but you want to self-host, Rivet.dev by Nathan Flurry is a very nice open source alternative to durable objects. So we thought it would be cool and useful to put a Git server inside a durable object and store one repo per durable object, and this is how we've done it. So when starting a project like this, there's always a choice of what open source library to leverage and what to build from scratch. Git is sufficiently complex that building its mechanisms from scratch exceeded the scope of this project. Also, we quickly learned that porting Git proper to WebAssembly would be almost impossible due to Git lacking a clear programming interface because the source files are tightly coupled. We judged that there were two legitimate libraries we could use, libgit2 or isomorphic Git. Both are amazing projects ran by incredible people. It seemed to us that libgit2 is 1, more battle-tested, 2, more robust, and 3, implements more core Git APIs, so we chose to go with it. I have to say that working with libgit2 is a joy. I want to give a shout out to Ed Thompson and the other libgit2 maintainers. The official website provides many examples to get started. The reference section is very detailed, and most of all, the code base is surprisingly legible, given that it's written in C. An interesting learning from reading many open source code bases, including libgit2, while doing this, is that in the era of AI coding, deep understanding is the key. Don't be afraid to read the code of well-crafted open source projects, especially now that tools like Claude Code or Codex or OpenCode are widely available. Fire up these tools in an unfamiliar code base and just ask questions. And I would argue that in some code bases, this could be a better use case for AI tools than having them write code directly. To compile our libgit2-based Git server, we used mscripton, a powerful compiler for C and C++ to WebAssembly. Setting up a compiler toolchain is possibly the most boring and tedious part of the work. It involves a lot of reading the documentation, toggling configuration flags, writing scripts, and rerunning the build processes. Also, once the initial setup of the build toolchain is complete, the work is not done. Considering that we're targeting a resource-constrained runtime, during the entire implementation of our app, we needed to keep a keen eye on the resource utilization for typical use cases. So we made many fine adjustments to the build toolchain. So one, we tuned the memory footprint. So this is something that's hard to guess correctly up front. It requires a lot of trial and error, logging, and using the browser dev tools to profile the app to correctly adjust the stack and the heap, memory reallocation, etc. So we tuned the lifecycle of our WebAssembly code, meaning how we instantiate and run WebAssembly. So before, initially, shown on the left side, we've gone with the simplest approach of instantiating the Wasm code on each incoming request. This works fairly well, but it's wasteful. So after keeping in mind that durable objects act as mini computers that get booted up on each request, on the right, we show that we ultimately move to instantiating our Wasm code whenever the durable object starts, and then we reuse the same instance for each subsequent request. This is not entirely straightforward to do, since it requires that our Git server, which is written in C, correctly cleans up after itself to allow for multiple invocations. We found Valgrind to be super useful for this purpose. So, we all know Git uses the file system for persistence. We're compiling our Git server to WebAssembly. For WebAssembly, there is a standard called WASI that, among other things, defines a file system interface. It's supported by some platforms, but in Cloudflare workers, it's in the experimental stage. The compiler that we used, mscripten, supports WASI, but it also defines its own file system interface. If we were building a platform, we'd look to use the standard interface, WASI, but since we were just building the file system for ourselves, we used the mscripten's interface directly. For storage, we used durable objects transactional storage. Unsurprisingly, we named the resulting file system DOFS. At the time of building this, durable objects had only an asynchronous API for working with the transactional storage. Since then, durable objects have received 2 synchronous APIs, and working with an asynchronous API represented a challenge. So the goal was to be able to read and write to the transactional storage from our Git server written in WebAssembly. mscripten's file system interface is synchronous. In general, mscripten allows 2 ways to run asynchronous code from WebAssembly, so asyncify and JSPI. To make the file system work, we dug into mscripten and rewrote all its file system APIs and made them asynchronous. The result was a working file system in durable objects that we can interact with from WebAssembly. Having an asynchronous mscripten file system API is very useful, since common storage options in JavaScript WebAssembly runtimes, including the browsers, usually have async interfaces to avoid blocking the main thread. For example, indexed DB and origin private file system. We didn't yet pursue this option, but we might sometime in the future. So, who's familiar with the term CGI? If I can get a show of hands. Nice. So CGI is an interface specification from the early 90s that describes how a web server can handle a request by executing a binary and sending back a response. Our Git server uses a CGI-like interface that invokes the WebAssembly code instead of a native binary. What's very cool about this approach is how modern web APIs fit very nicely in this model. We use streams to efficiently handle HTTP request and response, and we map these streams to standard input and standard output of the WebAssembly program. This means that we can very efficiently utilize the limited resources available in each V8 isolate by buffering as little as possible. As many of you already know, Git has 2 primary strategies for syncing a repo to a server, the so-called dumb protocol and the smart protocol. Historically, dumb protocol came first. It exposes Git objects and refs in the same form as they are stored, without transformation. It's reasonably simple to enable on the server side, but it's inefficient. And then on the other hand, the SMART protocol was implemented later, and today it's practically the standard. SMART protocol tries to minimize the amount of data transferred during the sync. The drawback, however, of this protocol is that it requires a negotiation step between the client and the server over a full duplex channel, and it can be CPU intensive to compute the difference that is sent over the wire. All modern Git servers use the SMART protocol, so we chose to implement it as well. SMART protocol is implemented as part of Git send pack and Git receive pack for handling Git push, and Git fetch pack and Git upload pack for handling Git fetch and Git clone. It really helps that libgit2 robustly implements a vast array of the Git internal machinery and makes it accessible through a nice API. libgit2 is just amazing. So even though the SMART protocol is described in very few places, most notably the Git repo itself and the indispensable pro-Git book, when implementing the server, reading the Git source code and employing reverse engineering techniques is unavoidable. Still, there is a development technique that makes building something like this much easier and less error-prone. It's the extreme version of the approach I've heard described as first make it work end-to-end, which I'd attribute to Rita, who's part of the Cloudflare team. So we call this technique building a rope bridge. So allow me to take a slight detour to illustrate why. So my mum is originally from Peru, and back in the day in Peru, the Incas mastered a beautiful technique, as you can see, of building rope bridges. Unfortunately, there are no more rope bridges that are in use today due to various reasons. So I think this ancient technique is very beautiful and instructive. First, the builders pass a single thin but very long rope over the river. They then use this long thin rope to pass several thick ropes over it that will serve as the backbone of the bridge. 2 ropes for the handhold and the remaining ones for the floor of the bridge. Finally, the builders carefully productionize the segments of the bridge, starting from one side by braiding together the thick ropes that are the backbone of the bridge. What's interesting to me about this approach is that in each step of the process, there's a bridge that connects both sides of the river. It just wouldn't pass the integration tests until it's complete. Our approach to implementing the SMART protocol for our Git server was analogous in a way. We started with a working Git server. In our case, we chose Node Git server from GitHub, which is an open source implementation of the Git server for Node.js. We incrementally removed all features except for the core functionality that ultimately fit in about 80 lines of JavaScript for Node.js. This core functionality leveraged Git receive pack and Git upload pack commands of the native Git binary. We incrementally replaced these commands with our implementation that utilizes libgit2 instead of Git. Finally, we ported the wrapper code from Node.js to Cloudflare Workers and compiled the libgit2 equivalents of Git receive pack and Git upload pack to WebAssembly. So the key was to methodically break down the process into small incremental steps and keep iterating on the rope bridge, keeping it functional in each step until the last one when it finally becomes usable. To make our WebAssembly server useful, we're compiling and linking a few more libraries alongside libgit2, most notably zlib, libarchive, and libmagic. So considering that our build process consists of compiling the patched mscript and compiler, compiling libgit2 and other libraries, and compiling the Git server to WebAssembly and linking it with libraries, this build process is quite complex. If we resorted only to the traditional build tooling, such as shell scripts or makefile or some other build system, it would be really difficult to keep it robust and repeatable. Fortunately, Nix exists. It's amazing and it's super useful here. With Nix, it's possible to describe the entire build process as a collection of declarative Nix scripts. We can build the resulting WebAssembly in one step from scratch, or incrementally and have the opportunity to intervene in the process. Not only that, but because we're using NICs, the compilation targeting native architecture or fine-tuning via compilation flags is also very easy. So, after we've built a working Git server in WebAssembly, we've invested a lot of effort into optimizing it to achieve amazing performance in a serverless environment with constrained resources. First, we optimized the size of the deployed code by compiling all libraries and our server code with flags that minimize the size of the produced output. During bundling, we also incorporate the libmagic's binary database for recognizing file types into the final code bundle. By default, this database is unacceptably large, but fortunately, it can be trimmed significantly by excluding file type detection signatures for less relevant file types, so we've done this as well. To ensure that our Git server durable objects can serve many concurrent requests in parallel, we've implemented caching strategies across the stack. So one, we've created a component we call consistent cache that leverages the durable objects transactional storage for consistency and the Cloudflare data center scoped cache API available in each worker for caching request response pairs. By default, cache API is eventually consistent and wouldn't be useful on its own, given that we want writes to the repo to be reflected immediately. In addition to caching, consistent cache also enables concurrent request deduplication. This means that two or more concurrent read requests with the same parameters result in only a single request to the WebAssembly Git server. The Git server then produces a response that we clone and forward back to each client. We also created our own storage engine. This component replaces the in-memory caching functionality that each durable object has built in by default. This was necessary so we could precisely control which data chunks are cached and when to evict them from memory. Basically, it allows us to programmatically specify the caching strategy. So, removing mmap. libgit2 uses memory mapping and map system call when reading and writing objects to pack files. This is a good default for typical environments that libgit2 is designed for, but it's not a good match for our resource-constrained serverless environment. So memory mapping basically means that the program maps a part of a file or the entire file from the persistent storage into the memory. As a result, the programmer gets a more convenient programming interface and a performance boost. Unfortunately, memory mapping doesn't pair well with a binary produced by mscripton, since it results in an additional copy of the file in memory. This is a problem when libgit2 memory maps bigger pack files. We've tried to modify mscripton to adjust this behavior, but it proves simpler to modify libgit2 to remove the use of memory mapping altogether. The result is that our Git server reads from the storage only the exact parts of the pack file that it needs. So read requests that previously took 3 seconds in a bigger repository now take about 100 milliseconds. So when the Git server handles an incoming request, it almost always needs to know the contents of some files and directories in the repo. So it makes sense to always preload these files and directories from the storage into memory when the server is started. We do that by preloading all directories, all pack index files, config, fetch head, and packed ref files. And we also preload just the inodes of all pack files to make the subsequent reading of their contents quicker. Finally, if there are many writes to the Git repo, this can result in a large number of loose objects or in a moderate number of smaller pack files, which are collections of objects. This impacts the performance of the repo, so we came up with a pack file repacking strategy that provides a balance between the total number of pack files and the work necessary to repack them. So, remarks about Git that we hope to address in the future. So while building the Git server, we encountered a few issues that I would like to mention briefly. So one, Git Smart protocol for syncing via fetch and push requires a full duplex channel for communication. This is needed so that the client and the server can negotiate the minimal pack file that will be sent from one to another. Unfortunately, the underlying transport mechanism that our Git server relies on, browser's fetch API, is not full duplex. In practice, this means that we cannot have multiple rounds of negotiation between the client and the server, so we can't git fetch from our Git server if the repo has too many refs. This is an insufficiency in the browser's fetch API, but it also seems like an inconvenience in the smart protocol design. So this design seems like a result of a time when bandwidth was comparably more expensive to CPU cycles. It would have been amazing if there was an alternative mechanism in the smart protocol that wouldn't look to minimize the size of a pack file completely and would potentially be more CDN and cache friendly. I know it's kind of hard. We've been wrestling with how this could be possibly achieved ourselves, but we don't have a better solution. So after building an infinitely scalable Git server infrastructure with our serverless Git server, we decided to build a multiplayer coding infrastructure that would accompany it. The guiding idea was to create a system that would allow collaboration and would tightly integrate with Git. With that as our goal, we've built a multiplayer POSIX-compatible file system by combining YJS, WebSockets, and durable objects. The file system now powers our collaborative coding editor, in which we've enabled many interesting features, like committing editor contents to the repo, importing from anywhere, including GitHub, anywhere on the web or a personal computer, multiplayer collaboration on Markdown, multiplayer drawing with TLDraw, AI editing, and one-click global deployments to Cloudflare workers, all of this combined with Git repositories. So we launched our initial iteration of the platform in May, and ever since then, we've been busy improving our product based on the feedback we've received from our users. We've made many incremental improvements, but we also realized that a major change of direction was needed. So I'm happy to say that we're a few weeks away from relaunching GitLib with many fundamental improvements, the biggest of which is our revamped multiplayer file system. This new iteration will feature enhanced support for agentic coding, copy-on-write semantics across the stack, offline support, time travel, and it will be super lightweight. Our mission is to build the best multiplayer agentic coding platform in the world with Git and serverless as the main building blocks. Thank you so much for listening.